Welcome back, everybody. Okay, so now, before we go into the next application, we're going to look at a particular corollary of compactness that many of the applications are going to come in the form of this particular result. And it's essentially something that is equivalent to compactness. Actually, when we prove compactness next month, we're going to prove this result first, and compactness is going to follow immediately from this result. So the result says the following. Suppose we have a set of sentences, gamma, and imagine that it's an infinite set of sentences, and that all together imply phi. Okay, so this is a logical implication. So this says that every model of all of the sentences in gamma at the same time, every model of gamma is a model of phi. Okay, and what the theorem says is that then there has to be a finite subset of gamma that already implies phi. So you didn't need all of gamma to imply phi. This is a finite subset that implies it already. Okay? So such that all the models of this gamma 0 are already models of phi. So you don't need, like for logical implication, you don't need infinite set of sentences. Finite sets are enough. And if you were using an infinite set, well, actually a finite subset would have been enough. And we claim this is equivalent to compactness, and this is because of the observation that we had before, that we said that gamma logically implies phi. This is equivalent to saying that the set of gamma together with the sentence not phi is not satisfiable. Right? You recall this from last week? Now, compactness tells us that if this is not satisfiable, then there must be a finite. Compactness tells us that if this set is not satisfiable, there must be a finite subset that is not satisfiable. And we may assume the subset contains not phi. Right? So compactness says that the opposite, not the contrapositive. If every finite subset is satisfiable, then the whole thing is satisfiable. So if the whole thing is not satisfiable, then some finite subset must not be satisfiable. And actually, this is an if and only if, because if the whole thing is if some finite set is not satisfiable, then of course the whole thing is not satisfiable. Just adding more things. So actually, this is an if and only if. Now, the same observation that we mentioned before about this finite set, I'm just going to copy this part. Right, so here, remember from the same argument that we did up here, we got up here that gamma 0 union not phi is not satisfiable if and only if gamma 0 logically implies phi. All right, so that's what we're using right here, same argument as above. And now that we have that these three all implied are equivalent to each other, then we get therefore that these two are equivalent to each other by going around the circle, right? So a formula set of sentence gamma implies phi if and only if some finite subset already implies phi. That's what the theorem says. Okay, let's see how we can use this in applications. So here's the first one. Suppose we have a sentence phi that is true in all infinite groups. This is a sentence phi, first order sentence in the vocabulary of groups, and you somehow prove that it's true in all infinite groups. Now, what we claim is that it must be true in some finite group also. Okay, so if you prove that something is true in all infinite groups, it must also be true in some finite groups as an application of compactness. Well, we get a bit more than that. We just actually get that there must exist an n such that every group that has size at least n satisfies phi. Okay, it's quite interesting. So if you can prove that phi is true in all infinite groups, somewhat, and phi is the first order sentence, then it must be true on all groups that are sufficiently large, size larger than some n, for some finite n. Okay, so even though you didn't prove anything about the finite groups, compactness is going to get you the result for finite groups that are large enough. Okay, so let's recall what we usually have when we deal with groups. We have the vocabulary with an identity and an operation. We have the three group axioms that are like associativity, identity, and the inverse axiom. And then let's consider this set of sentences T that on top of the group axioms, it has these sentences phi sub n for n the natural numbers, where phi sub n is a sentence that says there exist n different things. So the group has size at least n, right? So the way we say that is there exists x1 up x2, x3 up to xn, such that they are all different from each other. So you have to write here the whatever n times n plus 1 over 2 little atomic formula that say that all the possible combinations of two of them are all different. Okay, x1, x2, x1, x3, x1, x2, x3, x1, x4, x2, x4, x3, x4, all the combinations, all the pairs are all different to each other. So that's, you can write that as a sentence and put all these sentences together, and we have that the group has to be infinite, right, to satisfy all these. And exactly the infinite groups are the ones satisfying these, right? So this says there exist at least n different elements in the group. To satisfy them all at the same time, you have to be infinite. Okay, so yeah, we mentioned this before. So this is the class of infinite groups, which is weakly elementary. Let's prove the theorem. If something is true in all infinite groups, then what we know is that T, which is axiomatized in all infinite groups, logically implies phi, right? Because every infinite group, every model of T is an infinite group, and we prove that phi is true in all infinite groups. That's what it means to logically imply something. And by our theorem that we proved before, if you have that a set of sentences implies phi, then there must be a finite subset of it that already implies it. By compactness, we know there exists a finite subset T0 of T such that T0 logically implies phi. And here by compactness, when I say compactness, I don't mean the version of compactness about satisfiability, but I mean this corollary of compactness, which is also called compactness because as you see here, like they all imply each other. So all these things are all equivalent to each other. So they are essentially the same. So they are both called compactness. Okay, and then this T0 is a finite subset of T, and this one is T. So that means that in particular, so for some n, we must have that T0 is a subset of these guys and some finitely many of these guys, right? Yep, so that has to be the case because it's just because it's finite. And then what do we have? Then we have that groups model phi, right? And what does it say that these guys logically imply phi? Well, it says that what are the models? The models of these? The models of these are the groups of size bigger than n. That's exactly what the models of that are. So every group of size larger than n is gonna satisfy phi. Okay. So it's a quite interesting corollary, right? So if you can prove something for all infinite groups, it's true for all groups of beyond a certain size. Very well. So let's look at another application of this version of compactness, and it's to show that certain classes are not elementary. Or we already saw an example where we showed that a class was not weakly elementary, so there was no set of sentences at all characterizing them. Now we want to show that exactly this one, the class of infinite groups, which it is weakly elementary because that's right there. You can see the axiomatization for it. So this set of sentences are the ones that characterize infinite groups. But there's we need an infinite set of sentences, right? We need one phi of n for each natural number, and elementary meant that there are finitely many. And here we're going to show that finitely many are not enough. Actually, elementary means one, right? Because if you have finitely many, we can put an and between all of them. So there is no one single sentence that is going to axiomatize infinite groups. And why is that? Well, it follows exactly from what we had before, right? So if psi was true of all infinite groups, if it's a potential axiomatization for all infinite groups, psi must be true of some finite group. That's exactly what we had in our previous slide, right? So there cannot be a sentence that one single sentence that characterizes all infinite groups. So the class of groups is not weakly elementary. Okay, so that's good for this week about compactness. Next week we are going to look at compactness on sentential logic. This is the logic we saw at the beginning of the course, propositional logic, which is much simpler. It still has some nice applications in that case. And the advantage is that we can prove that one easily. Well, not that easily, but we can do that next week. Not like this one, which we're going to prove later in the semester. See you guys later.